looking at determinants, coming up with a function. And again, the idea behind it was to come up with a numeric check for how to determine whether or not a numeric, it's a function. We motivated it through volume. But the idea behind this is one of the properties is to come up with a numeric check for whether or not a matrix has an inverse. And we kind of guessed at it from what our formula is for the inverse of a 2 by 2. So just to remind again, hey, if you have a 2 by 2 matrix, A, B, C, D, and you want its inverse, how do you take the inverse of a 2 by 2? Where does that go? Yeah, it's 1 over that, right? And then it's multiplied by what? Good. So that's just reminding again how we calculate the inverse of a 2 by 2. Notice this AD minus BC is in the denominator here. And if you look at the determinant of the 2 by 2, that's exactly how we calculate the determinant of a 2 by 2 matrix, right? So notice, what aren't you allowed to divide by? 0, right? So we have this numeric check, if you will, at least for the 2 by 2, that tells us whether or not we have an inverse for that particular matrix. We'll have an inverse if that's not equal to 0. We don't have an inverse if it is equal to 0. So that's exactly where we're headed in this section. To get there, though, let's talk about a couple of theorems here. Well, basically what we're going to do. Talk about a couple of theorems here that allows us to talk about this idea with the determinant. So the theorem is that we have a non-singular matrix. Non-singular means, again, what? It has an inverse, right? Good. It's invertible. Good. So then the actual theorem here is that your determinant of A is not equal to 0. All right, so let's talk about why this is true. Well, if it's non-singular, then what do we know can happen with when we row reduce it? What do we get to when we row reduce? The identity, right? So the reason why this is going to be true is that if A is non-singular, are there extras of the 3.4 handouts? Because, oh, there's one there. Good. It looks like I'm out, and I don't know if they shouldn't be out. That one too, and that one too. There you go. Yep. All right, so if A is non-singular, we know we can row reduce it to the identity. What can we use to accomplish row operations? What can we use to multiply to accomplish row operations? Elementary matrices, right? So let's call them E1, E2 out to En, so that if I take the E1, E2 all the way to En and multiply by A, we get the identity, right? Basically, we're just saying if it's non-singular, if it's invertible, then it's row equivalent to the identity. There's a sequence of row operations that take us to the identity, and we can accomplish that sequence of row operations through matrix multiplication with elementary matrices. That's stuff we talked about for the exam, right? Okay. What do we know? What do we know happens to the determinant every single time you multiply by an elementary matrix? For example, if I multiply the elementary matrix that's just a constant times a row and multiply by a matrix, what does it do to the determinant? Changes it by The constant, right? Good. So it changes it by the constant. We know that constant is non-zero, correct? Okay. And likewise, if we do a row swap, what does that do to the determinant? It makes it negative. And if you do the constant multiple of one row added to a second and replace the second, what does that do? Nothing, right? So when I look at the determinant, if I do the determinant of both sides here, they better be equal, correct? If I do the determinant of E1, E2 out to En times A, that better be the determinant of I. What's the determinant of I? 1. Right? Get all the way down to 1. Pardon me. So think about what the determinant does. We know that this determinant just either it multiplies it by a constant, it makes it negative, or it keeps it the same depending on the row operation, right? Okay. So if we started with a 0, if the determinant of this were 0, would I be able to change it to a 1 by doing any of those operations? If the determinant were originally 0, and I multiplied a row by a constant, it'd still be 0, wouldn't it? If I swapped the two rows and took the negative, it would still be 0, right? And so on down the line. And if we did the third one, it wouldn't change it at all, so it'd still be 0. So if the determinant of A is equal to 0, then the determinant of E1, E2, En times A would still be 0, right? Oops. Since the elementary matrices wouldn't change the determinant. Oops. The only way it could change it, notice that the only way it could change is if it actually added something to it, right? It's every change is a multiplication. It's either multiplication by a constant or multiplication by a negative. -1. Well, that still would be 0 in any of those cases. So hence, we must have determinant of A is not 0. All right. Well, what happens if it's singular? Singular means it does not have an inverse. Good. So if the matrix does not have an inverse, and you go through your row reduction, what has to happen at the end when you put it in reduced row echelon form? What do you have to see when you get it in reduced row echelon form if it's not invertible? What has to appear? A row of zeros, right? What happens if you get a matrix with a row of zeros in it? What does its determinant have to be? It has to be 0, right? For several reasons, right? If you've got a row of zeros, then there isn't any dimension that's given by that row, so the volume would have to be 0. Or if you think about it by doing cofactor expansion, expand along that row, you'd multiply each of your minors by 0, each of your cofactors by 0, right? Okay. So the theorem here is that the determinant of A really is 0 in this case. It's the same proof essentially. So we're going to use a sequence of elementary row operations, a sequence of elementary matrices. All right. So we'll put the matrix A in reduced row echelon form. And we've already said that this will have a row of zeros. All right, so now let's just think about what has to happen. We just said a minute ago that at that point, the determinant will have to be 0. If we get down to a row of zeros, if we get our reduced row echelon form down to a row of zeros, that matrix has to have determinant 0. So if I use this sequence here with my E1 out to En, put my A in reduced row echelon form, and I get a row of zeros, the determinant has to be 0. But let's think about what happens on the left-hand side here. No matter what, I can break up this determinant over this product, because think about what happens. If we know what happens to, if we know E1, for example, is a constant times the matrix, then we know it's, or multiplies a constant times a row, then it changes the determinant by that value, right? And so on down the line. And essentially what we can do is just break this up over the product. It's a bunch of steps to do that, right? Say E1 is a constant times a row, then it's a constant times the determinant, but the determinant of that E1 will just be the constant, so I'm just replacing it each time. So the determinant behaves nicely with respect to that product. Now I've got a product of a bunch of things that equal 0. If you have a product that equals 0, what has to be true about the about something in the product? If you have a product that equals 0, what has to be true? At least one of them 0, right? When you do a determinant of an elementary matrix, do you ever get 0? No. So since each of those determinants is not 0, we have that the determinant of A must be 0. So these two theorems give us that numeric check that we were talking about. Determinant not 0, matrix has an inverse. Determinant is 0, matrix does not have an inverse. Notice that basically in both cases, we're using this nice property that if you've got a sequence of elementary row this product with a bunch of elementary matrices, I can just break this up over the product, right? Well, that gives us a next nice property of our determinant, that if you've got two matrices, then the determinant breaks up over the product. And the idea here is just use a sequence of elementary row operations. So let's just worry about whether or not A is invertible. So let's start with A as singular. What did we just say that the determinant of A is? Okay, good. All right. So if A is singular, pardon me. If A is singular, we know that when we do the reduced row echelon form of A, we get a row of zeros. Oops. Right? We agree? Okay. So, again, if my E1 to En is that sequence of row operations that gives us a row of zeros, what's the determinant of this going to be? If I use E1, E2 out to En times A to put it in reduced row echelon form, and I get a row of zeros, what's the determinant of this whole matrix going to end up with? It's going to be 0, right? Because one of our homework problems we did before is that if you take a matrix with a row of zeros and multiply it by any other matrix, you still get a row of zeros, right? So this determinant will be 0. But we just said a minute ago that I can break up the determinant if I over those elementary elementary matrices. I mean, and now what do we have again? Just like in the previous case, I've got a product that equals 0, right? Okay, can these be 0? No. So that determinant of AB has to be 0. And by default, that equals determinant of A times determinant of B, because we said determinant of A was also 0. Right? Right. The other case, A is non-singular. We know that if a matrix is not singular, then we can write it as a product of elementary matrices. That was one of the things that's equivalent to being invertible, right? One of the things in the Vega theorem is that I can write it as a product of elementary matrices. So if I look at the determinant of A times B, I can replace the A with the product, right? I can replace the A with the product of the elementary matrices. We just said a minute ago that I can break that up nicely. This way. Oops. So I broke it apart, pulled the B off, but now I can take this thing and just put it back together again. So this now becomes determinant of E1 out to En times determinant of B, which is this determinant of AB times determinant of B. The whole crux of the proof in all of these things that we've been doing is that the determinant function behaves nicely with respect to multiplication by elementary matrices, and we put in all of that groundwork already last week when we talked about what elementary row operations do to determinants, and then realized that we can do elementary row operations through matrix multiplication. All right, so 2 big things on this particular page, more than the proofs. I wanted to go through the proofs anyway. But the 2 big things on this page is, 1, determinant gives you a numeric check, right? You can check to see if a determinant or a matrix is invertible by looking at its determinant. Okay. The second thing is that determinants break up over products, which is a nice property. Do determinants break up over sums? No. Okay. Remember, the determinant property that involved sums were identical matrices everywhere except one row, and those rows were added, right? It's a very specific thing, not matrix addition. Okay. All right. So let's see if we can do this and talk about using these things and using some of what our knowledge is of elementary row operations to see if we can come up with some other properties. You just told me that if we multiply a single row by a scalar, it changes the determinant by that scalar, right? And we did some problems where we evaluated determinants through row reduction and popped those constants out in front. And we're doing that last week. Okay? All right. What happens though when you multiply the matrix by a scalar, the entire matrix by a scalar? Do we just multiply by one row by the scalar? No, you multiply every single row by the scalar, right? So what's that going to do to the determinant if you multiply every single row by a scalar? It'd be C to the n, right? You'll take row 1, multiply it by C, row 2, multiply it by C, 3, and all the way down. You've got n rows. So when you multiply a scalar times a matrix, you can pull the scalar out of the determinant, but you have to do it n times. It has to come out of row 1, it has to come out of row 2, it has to come out of row 3, all the way down to has to come out of row n. Okay? Yes? It's not the same thing as C times the determinant of A, no, because the constant has to be multiplied by every single row. Right? Remember when we did the row operation stuff? If I had a 2, 4, 6, 1, 8, 2, 5, 4, 3, something like that, we said we could pull the 2 out of the top row, but notice that it doesn't change the rest of the matrix, right? This is saying I'm pulling the constant out of the first row and out of the second row and out of the third row and so on down the line. Let's try a different thing. Say something like this. Okay. This would be 1, 2, 3. I haven't pulled it out of the next one, right? I only pulled it out of the first row. And then I have to pull it out of the second row. Right? All the way down. Okay. So it's going to get multiplied all the way out in the front every single time. Okay. What do you think happens if you have an invertible matrix and you do the determinant of A inverse? What do you think the determinant should be? Went over. Well, I'm not using a C anymore. I'm just looking at the matrix A. I'm agreeing with the 1 over part. Let's try it this way. What's the determinant of the identity again? 1. What's another way? If I know that I have an invertible matrix, what's another way I can write the identity? If A is invertible, what's another way I can write the identity? If A is invertible, it's A times A inverse, good, right? You do that when you get common denominators, right? You multiply by 1, fancy, don't you? 3 over 3, same concept, right? Okay. What did we just say we could do with a determinant with respect to a product? Split it. And then if A is invertible, what do you know about the determinant of A? If the matrix is invertible, what do you know about the determinant? It's non-zero. If it's not 0, what can I do with the number? Divide, yeah. So this will be 1 over determinant of A. Yeah. Knowing that it's non-zero allows me to divide by the number, right? So I do the determinant of A inverse. It must be 1 over the determinant of A. The next one's more of a think about it type of idea. Remember, one of the ways that we can calculate determinants is through cofactor expansion. And remember, when we do cofactor expansion, you can expand along any row that you want or any column that you want, right? What does a transpose do to a matrix? Flips the rows and columns, right? So if you chose to expand along the row of A, you could have expanded along the column of A transpose and get the same answer, right? So when you transpose a matrix, it's not going to change the determinant at all. Does that make sense? Okay. So let's see if we can put these properties to use. Let's say you have a 5 by 5 matrix. You know that the determinant of A is 13. First problem asks you to figure out the determinant of A squared. What's that going to be? Maybe 169. Why is it 169? Yeah, 13 times 13. Exactly. That's exactly right. You can remember we can break up determinant over a product, right? A squared means A times A. So you do determinant of A times determinant of A. 13 times 13 is 169. Does that make sense? Okay. Now notice that the fact that it was a 5 by 5 matrix had nothing to do with this part. It does in the next part. I have 6 times, determinative of 6 times A transpose. In order to pull that 6 out in front, what do you need to do? Good, 6 to the 5th, right? Because it's a 5 by 5. Okay, I've got to pull that 6 out of every single row. There's 5 of them, right? And just a second ago, what did we say the determinative of transpose is? Same, good. So this is 6 to the 5th times determinative A. So you get 6 to the 5th times 13, and I'm not doing it in my head. So that's what a calculator's for. That part okay? All right. The next one uses the same concepts, but just reminds us of a different property of inverse. Notice I've got my 5 inside the inverse, right? So if you want the inverse of 5A, what do you do with the 5 with respect to the inverse? It'd be okay. So yeah, let's take care of the 5 first, and then worry about the determinant. To take care of the 5, since it's inside the inverse, it becomes what? 1/5 A inverse, right? Because it's going to invert the constant. Yeah. And then now you can pull the constant out, so it becomes 1/5 to the. What happened? What do we need to do with the? Oops. What do we need to do with the 1/5? To the 5th power, right? Because I got to pull it out of each row again, right? Because it's a 5 by 5 matrix still, right? Yep. Okay. Well, that one I can do. That one I can do in my head. What's the determinant of A inverse? Yeah, it'd be 1/13 in that case. And I'll leave it to you to do the 3125 times 13. That okay? All right. I don't remember what part we are on, what letter we're on in the mega theorem, but you've got another one that you can add. What letter are we on? G? That's what I thought it was, but and you can probably guess what it is. What's our numeric check for whether or not a matrix is invertible? The determinant is not equal to 0. Good. So that's another equivalent condition that you can put on your mega theorem. We're up to 7. Only 13 more to go. I'm not kidding. We'll get to 20. All right. That's all right? Any questions on those properties at all? You'll notice that those properties you'll play around with on the homework too that I handed out there. All right. So let's go to the next section here, where we've got some applications of determinants. Pardon me. I'm sorry. Goodness. All right. So this next definition is going to look a little bit goofy and may not make a lot of sense for why we even care. But there is an application of this particular matrix to solving systems of equations. And again, like I mentioned before, linear algebra is based on solving systems of equations, right? So it's a nice application of doing determinants this way. All right, so we talk about what is the adjoint of a matrix. So remember, when we did determinants, we talked about the minors, right? The minors were the determinants of those submatrices that you made by removing a row and a column, and then the cofactor was just making it positive or negative depending on where the minor was, right? Okay. So the adjoint is referred to as the transpose of the matrix of cofactors. Okay. So rather than writing out longhand what it has to look like, let's do this with an example. Okay. So here's my matrix A. Remember there's 9, well, it's a 3 by 3, so there's 9 cofactors here. There's a cofactor associated with every single entry in the matrix. Okay. When we form the adjoint, we're not worried about what the constant is that the entry is that we're forming the We're not worried about the entry that we're removing that row and that column to form the cofactor. We're just literally looking at the cofactor and going to put that into the matrix. Okay. All right. So we've got C11, C12, C13, C21, C22, C23, C31, C32, C33. Okay. All right. So when I remove row 1, column 1, we're left with 1, I said 1 in row to 3. 1, 3, 0, negative 5. Right? Now again, remember, cofactor also puts in the sign, right? Will it be a positive determinant here or a negative determinant based on where we went? Positive, right? Because we're up in the upper left-hand corner. That'll be a positive. And when you do the calculation here, we'll get negative 5. Yeah. Okay. What determinant do we do for the cofactor for row 1, column 2? I'm doing row, I'm doing row 1, column 2 this way. 3, 3, 4, negative 5. And will that be a positive or a negative? Be a negative, right? Because we moved over 1 spot. Okay. Negative 15 minus 12 is negative 27, but it'll be positive 27 in that case. What determinant do we need next? 3, 1, 4, 0. And is it positive or negative? Positive. When you do your determinant, you'll get negative 4. Another way to do your, whether it's positive, I talked about the sign board before. Another way to do it is add your subscripts, and if it's even, it's positive, it's odd, it's negative, right? Because we use that negative 1 to the I plus j. Another way to do it. Okay.
Wait, how do you get negative?
0 minus 4. You can look at the subscripts. If you add the subscripts and it's even, it'll be positive. If it's odd, it's negative. Yeah.
So it doesn't really matter like what the determinant is. Like it just matters the position for this thing, positive or negative. So, like,
correct. That's right. It just matters the position. That's exactly right. Yeah. It doesn't matter what the determinant is. You'll flip the sign accordingly if it's in a negative position. Yeah. That's right. 2, 1.
0, negative 1, 0, negative 5.
Is it going to be positive or negative out in front? Negative, but in this case, it doesn't matter because the determinant is 0. Good. 2, 2.
2, negative 1, 4, negative 5.
Positive or negative out in front? It's positive. They're going to alternate, right? I don't know. You get negative 6. I did my arithmetic right. The next one. 2, 0, 4, 0. This one will be out in front positive or negative. Negative, but it doesn't matter because, again, the determinant's 0. Almost done. Only 3 more to go. 3, 1.
2, 0, 3, 1. No. 0, 1, 0, 0.
Good. Yeah, because we're row 3, column 1. Yep. Positive or negative out in front? Positive, so we get 1 when we're done. The next one will be negative because it's going to alternate.
2, -1, 3, 3.
6 plus 3 is 9, so we get negative 9. And last one will be positive. 2, 0, 3, 1, and we get 2. Okay. Now notice that I wrote my cofactors vertically here as we were going across the rows. Right? I did C11, C12, Z13, writing it down. Right? Remember, the adjoint is the transpose of the matrix of cofactors, right? So I went ahead and just did the transpose as I was doing the calculations, right? I went, here's across my first row, so I'm making it a column now, right? Here's across my second row, so I'm making it a column. Across my third row, I'm making it a column. Okay? So I just wrote it that way so they automatically get my determinant. So my adjoint here, I can use the appropriate notation. The adjoint here will be -5, 0, 1, 27, -6, -9, -4, 0, 2. Okay. A good question. Why do we care? It's a very, very good question. Why do we care? It seems like a lot of computational work for some random matrix that we put up here, right? Okay. All right. So let's first take the original matrix, the 2, 0, 1, 2, 0, -1, I should say, 3, 1, 3, 4, 0, 5, and multiply it by the adjoint we just found. All right, let's look what's up in the upper left-hand corner here. I get 2 times -5, 0 times 27, -1 times -4. So I get -10 plus 4, I get -6. All right, let me do the row 1, column 1. Now do row 2, column 2. I know I'm skipping over some entries, but do row 2, column 2. What do you get? -6. Do row 3, column 3. Something's not right. I should get the same answer. Something's not right. Oh, it's because it's a -5. That's why. I knew something was not right. What do we get? We get -6. It doesn't seem like an accident. Let's think about why that has to be -6. Remember, these were your cofactors, right? Remember when we do our determinant, we do that cofactor expansion. What do you multiply by each of these cofactors if you were taking the determinant? Those entries that you expanded along, right? Right? I would do, if this is row 1, you would do 2 times that, 0 times that, -1 times that, doing the determinant, isn't it? This is why we do the transpose. When we take this row and match it with that column, I get the determinant. When we take this row and match it with that column, we get the determinant. When we take this row and match it with that column, we get the determinant. We should get the determinant all down the diagonal. Okay? Every single time when you do this multiplication. Now, I skipped over the other ones. Let's see what we get for the other entries. What do you get for the row 1, column 2? We get 0, don't we? What do we get in row 1, column 3? We get a 0. Row 2, column 1, get a 0. And you'll get 0 everywhere else. Okay? So in general, I don't know if I have it. Oh, good. I do have it on there. In general, notice this is the determinant. You could pop the determinant out in front and write this times the identity matrix, right? Okay. So this is true in general, and that's what the next property is on the next page, that when we have A times adjoint of A, it's the determinant of the matrix times the identity matrix. Okay? Okay? Now, I think it's pretty clear that the diagonal entry will be the determinant each time, right? Because again, if you think about, if I've got my matrix A, and I look at the ith row, then the ith column of the, pardon me, the ith column of the adjoint is exactly the cofactors that you would multiply by, right? That's how we form it, isn't it? We agree? That's what we just said when we did the numeric example, isn't it? So when you do the I entry of A times the adjoint of A is what? It's AI1 CI1 plus AI2 CI2 out to AIN CIN, which is one of the ways that we can calculate the determinant. We just saw that numerically, didn't we? Right? Because how did we get those cofactors? We went across the row, but we put it down the column, right? So it's just matching up the coefficients exactly like we would expect them to. Why are the other ones 0? That's weird. Why are the other ones have to be 0? That seems strange, doesn't it? I think it seems strange. Okay. So what if I had another one over here, just to write it off to the side? I had a CJ1, a CJ2, down to a CJN. Okay. That product would be AI1, CJ1, AI2, CJ2, AIN, CJN. It doesn't look like there's a lot there, right? But where would these have come from? Where would the CJ1, the CJ2, and so on down the line, where would those come from? How do you get the cofactors? What did we do to get all of the cofactors? What did we go across? The rows, right? We went across the rows, didn't we? So notice that we would have eliminated row J, but the row I still would have been in there, correct? Okay. So we can think of this as being the determinant. See if I can do this correctly. Let's say I had my AI1, AI2, AIN, and then I had an identical row down here. If you, this is say row J, if you expanded along this row, you would get those cofactors, right? It would be the same exact cofactors, because again, when you do your cofactors, you eliminate row and column, don't you? But you're left with the exact same matrices otherwise. What's the determinant of that matrix on the right-hand side? I've got 2 identical rows. If you have a matrix with 2 identical rows, what's its determinant? 0, yeah. So notice that when you do this computation where you've mismatched where the cofactors come from, you can create a determinant of a matrix with 2 identical rows and get 0. That's why all the other entries in that matrix are 0. Okay? because all the other entries can be thought of as the determinant of a matrix with two identical rows. Okay. All right. The important part here, at least in my mind, the important part here is this cool formula. It's a very cool formula. It also gives us another way to calculate an inverse, because if A is invertible, what do we know about this number right here? It's 1, right? Or not 1, it's not 0, right? Yeah, it's not 0, so I can divide by it. And if A is invertible, I can take the inverse, correct? Okay, so we can solve for A inverse in that formula. You get 1 over determinant of A times the adjoint of A. So, in the previous example, we found the adjoint. Let me go grab it so I don't have to rewrite it. Maybe. Eventually I'll get there. Oh, no. I lost the... Well, at least I can see it. The adjoint... Didn't have to remember what it was. The adjoint of A is negative 5, 0, 1, 27, negative 6, negative 9, negative 4, 0, 2, right? And when we did that product, we got negative 6 down the diagonal, so we know that the determinant's negative 6. So A inverse here will be negative 1/6 times that adjoint. There's our formula for the inverse involving the adjoint. Does this seem like a way that you would want to calculate an inverse? No, it's a lot of computations, right? So it's not an exceptionally useful formula in terms of calculating the inverse, but it's a nice formula for what we're going to do in for one of our applications for solving systems of equations, which is called Cramer's rule, and we'll talk about that on Wednesday. Right? So I know that there was some conceptual stuff here. Make sure that you know what the properties are. I'm not asking you to reproduce the proofs. Just want to make sure you understand what the properties are that we came up with. Okay, so determinant properties that we talked about and how to calculate adjoint. All right, and then we'll talk about how we do Cramer's rule next time. So have a good one.